And here we are. Hey, Thomas, you're
Hey,
typing. You're typing. Does it mean we're not ready? Yes, it exactly does. It means that.
right.
We're good. We're good. Look at this. The sun. It's beautiful. After
Yeah,
weeks of rain here in Italy, it was as I already expressed, it felt like being in London all the time. Whereas in London it was sunny. It was not the way it should be. But now it's getting nice, which is great. Um, what else? Another thing. Let me see if I can share. I got a new background for my iPad, and we'll start from there. Not from the background, but from the iPad, because we will talk about FSDP. But look at this,
yeah.
pure 80 OG nerd. I
Yeah.
see something that I owned
How many of
for
these are older than you are?
well,
That's the question.
maybe.
Not that
I
many.
don't know. No, not many. Older than me, probably none. Uh,
Yeah,
yeah, the CBM, I don't remember it in my childhood.
yeah,
And I don't remember the other controller, the video 2400. But I remember everything else. And that was very cool, very fascinating. The aesthetics of that Commodore monitor are something I would like to own one, honestly. Anyway,
yeah,
yeah, back when machines were dumb, right? Now apparently they are developing a mind on their own.
yeah,
And how do they do that? Through backprop. And today we'll talk about backprop, but not just that. We'll talk about large model backprop. So when you have a model that is larger than your GPU, you need to do something about it, which is do not get all your parameters in one GPU, but distribute it across. And so one of the standard ways of doing that, and there are many nowadays, many form of parallelism, but let's say one of the go-to ways of doing that for at least fairly moderate sized or models, or even largish models. But interestingly, with the new architectures and the crazy interconnects of the new clusters that NVIDIA is putting out, it's probably even going to work for even larger models, is FSDP. So, and we'll talk a bit about FSDP now, and then we'll also talk about how we interpret FSDP in the context of Thunder. Because FSDP is this mysterious thing that you enable on a model, you wrap a model with a call, you shard. But in the end, it's conceptually not super hard to understand. But also, it can be implemented as a trace transformation. And so we'll take a look at how we do that in Thunder. That, in a single file, you have all the transformations you need to apply to a trace in order to FSDP it. But there are many repercussions, and it kind of ties to what we were saying last week. So let's start by defining the problem, and then we'll proceed. So
yeah.
Thomas, stop me if I'm hallucinating as usual, and
Yeah.
and then we'll go from there.
So you have
All
a
right,
large model, right? Large.
exactly. There's a chunky model here, and we have GPUs. Let's say, we say have two GPUs here, and each one of them has some memory. So this thing cannot fit one of them, because otherwise we could do something called DDP, distributed data parallel. In DDP, you take a model and you have two GPUs, you allocate it on each one of them, and then you run the forward, you run the backward, and you run the forward, you run the backward on two different sets of data. So D1 and D2. So the batches are different. But the nice thing about that is that you will get gradients, gradient 1 and gradients 2, of course. Of course. in the back where you generate the grades, right? So at this point, since the data was different and we assume the model is the same, you get to a point where you have the weights are the same, okay? The G1 and G2 will be different. And so we want to run an optimizer step on that. But of course, we cannot just apply G1 on W, on the weights, and G2 on the weights. Otherwise, we will get different weights. Although there are schemes like DLoco, for example, that do that for a while, right?
Yeah, people try that, right?
Yeah, and it actually works, but it's not the topic for today. The classical DDP is that you apply the gradients to the weights after exchanging them, right? After synchronizing them. So you reduce the gradients and say, okay, machine B or GPU B, give me your gradients. I'll sum them together with mine, and at the end of the operation, we'll end up with the same gradients that are here, and then we can apply it to W, and this will lead us to have, let's say this was W step A, will lead to W step B, which are the same, and so on and so forth. So DDP is very nice because we can say, okay, now we have many of these GPUs or many of these machines, and the only time when we need to exchange anything is when we are synchronizing the gradients, when we apply the optimization step. Even when we do micro batching, where we compute the gradients on batches that are smaller than the batch size. So we keep computing the gradient, accumulating the gradient until we need to run optimizer step. At that point, we synchronize, but before with that, we don't. So it's very convenient, very low communication. Yeah, but what happens if we cannot load this model? Load this model on each GPU separately. Well, what we can do is to distribute the model across GPUs. And there are many ways of doing that. Today, we'll talk about FSDP, fully sharded data parallel. Fully sharded data parallel. So it's a data parallel, but it's sharded. And sometimes there's confusion with tensor parallelism, for example, where you take matrices and you split them up, right?
Yeah.
And you distribute them across GPUs. And then you will compute matrix multiplication in sharded form. And this is tensor parallelism. This is not data parallelism, right? In fully sharded data parallelism, you still compute all the matrix multiplications on the full parameters, right? So let's say you have one matrix here. Sorry, I keep on drawing boxes, but I know it's unimaginative, but it's okay. Let's say we have three big matrix multiplies, one after the other, and the model as a whole cannot fit in memory of one GPU. Well, what you can do if you have like 3 GPUs, for example, or 2 to make it simple, is we say, okay, GPU A, you will take the left side of the weights. GPU B, you will get the right side of the weights. But when it's time to compute, GPU A will ask GPU B for its side of the weights. So it will recombine just in time the full matrix, do the full matrix multiplication, and the same will happen in B. So for a single moment in time, A and B will reconstitute the full matrix by exchanging the missing parameters on each side. And of course, the data over which you compute that will be different because it's a data parallel, right? So it's just the same as this situation where we had 2 different data batches, right? So here, A and B will have 2 different data batches. But right before computing the matrix multiplication, they will synchronize the weights. And at that point, they will be able to compute the matrix multiplication, after which they can go back to this situation where A will only have these ones and B will only have these ones for this matrix. But at that point, you go on the next block. And in the next block, you will still exchange, reconstitute the full, do the matrix multiplication, and so on. So it's a kind of allocation, deallocation type of thing, right? So at every point in time, A will hold the whole model, but half of it, except the block that is being computed where it will get the full. But this will fit into memory. And yeah, and of course the communication is much more frequent because at this point, you need to communicate things back and forth. And you will think that, oh my God, this is a lot of communication. It is, but the advantage is that it can be overlapped. So while you're computing a matrix multiplication, you can start exchanging weights for the next one. And so you can have the communication computation overlap or computation communication overlap. Okay, so you overlap communication so that by the time you get there, you have the full weights and you can just go. And so if you tune things in the correct way, you will be able to distribute the memory across, the model across, and still do a data parallel strategy. Okay. So of course, there are a lot of details here that we're not talking about. Specifically, you can do different things like you can shard the weights. You can also shard other optimizer parameters. You can shard different things, the gradients. So there are different things you can shard. And you can go back to the deep speed papers on zero.
Yeah.
Deep speed zero. There's
Easy to
one.
forget that all these things were invented at some point, right?
Yeah. And then you can read in the paper. And then, of course, FSDP took elements of it and they're kind of the same idea. One extra thing that we can talk about right now is that sometimes you will hear the terminology hybrid. So hybrid strategy is, we said there's a lot of communication here, right? So every block potentially needs to communicate before computing. So there's a lot of like chattiness. And of course, if you have one big machine with a bunch of GPUs in them, and typically you have like up to 8, but with the new systems, the Grace Blackwell systems, you will have effectively 72 connected together, which is pretty incredible. But within the same machine, you have crazy memory bandwidth and communication bandwidth, right? So the bandwidth, the communication bandwidth between the GPUs is really important in this case because you keep communicating gigabytes of data. And so it makes sense to say, okay, if I have a single server, I will do FSDP, so fully sharded data parallel within the same server. But then I will do a more DDP thing across servers. So if I have 2 machines here, I will do FSDP here. So the model will be sharded across these GPUs. But then here, I will only, if I can afford it, I will only communicate across machines like I was doing here when it's time to synchronize the gradients. And this, the larger a single system is, the more sense it makes to go with FSDP on a single system. The last thing I want to bring up is, it's oftentimes we hear about tensor parallelism, other types of parallelism. They all have their own trade-offs. One thing that is a bit harder for tensor parallelism that we talked about above is that it's a bit harder to overlap communication and computation. Like in traditional tensor parallel, you cannot do that. So when you compute something that it's computed in a sharded fashion, and you need to reduce across all the ranks, the computation halts for this to get to the next stage. And so the trick there is try to avoid these operations that force you to reduce across as much as you can. And FSDP doesn't have this limitation, so it's kind of more, okay, fire and forget. You can just not take care of that at all. Awesome. So given this very kind of high level and hand-wavy explanation of how things work, now we can get more in the specific of what Thunder does, right?
Yeah.
So with Thunder, we know go ahead.
So one restriction that's important to keep in mind is that oftentimes, like, the model will not fit a single GPU even from the beginning, right?
Oh yeah,
So
that's right. That was a struggle
when
last
you're
week.
Operating, but right from the start. And I think that is something that kind of adds to the thing that you need to do, right?
Absolutely. And this is a big part of the struggle, honestly, because I had to scratch my head on how to do it, not with Thunder, but with the PyTorch, raw PyTorch the other day. I had so in PyTorch, you have two types of checkpoints. The distributed checkpoint. And then the traditional, like, single full checkpoint. This full checkpoint is it doesn't mean that it in one file, it just means that it's not already distributed across ranks. It means that it's one model with all the weights and maybe split up across different pieces of the checkpoint, but it's not in terms of material files, but it doesn't have the notion of being sharded. So each weight, it's in one matrix. And the matrix doesn't know how to shard itself across ranks, right? So it's one tensor. If I have a matrix of block A, the MLP, blah, 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 it will be one tensor. It will not be divided, right? So this is the full checkpoint that you download from Hugging Face. Now, you have it in your hard drive. You have GPUs that you want to load it on. And so what do? If you load it with torch load, you will go out of memory. One possibility is to load it on the CPU, but these models are so large that even loading on CPU, A, takes forever. B, you still have the problem of how do you then take it to the GPU? Great. So one thing you can do is to torch load with this the file name, and then say memmap equals true. And before that, you have the model that you put on device meta, right? And so model device meta will not allocate any tensor, even though it's gigantic. And then torch load and map true means that you can load the stick dict, but the stick dict will not have any bytes in it. The moment you access it, it will fetch it from this giant file or set of files where you memory map it. Means you have it in RAM. Like the RAM thing, the operating system thinks that you hold it in RAM. In fact, it's on disk. And so you will access each byte.
So basically, the operating system lets you say, this gets a memory address, but you don't load it actually.
Exactly. You just have the address. You know you can eventually get it, but you don't have it in front of you, loaded in memory. And so now you can then load the model, materialize it on the GPU on demand, and this will allow you to get it from the memory map file, and you can iterate parameter by parameter and load it. Now, what the problem is that if you already apply FSDP to this model, it means that the model itself is sharded, meaning each rank, each GPU only holds a shard of it, a shard of every weight. So if you try to naively load a weight in the model, it will tell you, oh, sizes don't match. Yeah, because each rank has a fraction of the weight matrix, right? So that's another complication. So you need to load and shard. So how to do that? We won't go too much into the details. Like with FSDP 1, it's practically impossible to do this. With FSDP 2 in PyTorch, it's possible, but you need a function that today doesn't live in the main PyTorch repository to shard the things. Like you need to know how to do, which is fine. We're chatting with the PyTorch team, and Alban told me the other day that they're taking care of making it a bit clearer, which is great. In Thunder, what we do is everything is a transform. And so what do we do in Thunder?
Yeah. So first thing is that you can actually hack up a thing that looks like loading a state dict, but it will just have promises of tensors.
Similar to this, right? It's similar.
Well, it's similar, but it operates at a Python object level, right? So we made a special not yet loaded tensor subclass of tensor.
Yep.
And what it does, typically when you load a state dict, at some point the parameters will be copied into the state dict that is there. And what we do is that we don't load the thing, but only load the tensor when it's copied to the state dict. And that works pretty well. And one reason why this works quite nicely is because in the PyTorch checkpoints are zip files. You can zip -L them. And so what happens is there is this pickled part, which is kind of the dictionary of the state dict, but then the tensor metadata, but then the tensor data itself, that will be in a separate file in the state dict. And that is a pretty neat thing. And that enables this lazy loading. And so
file or a section of the file, right? You could have a single file where you have the metadata at the beginning, and then the rest is this compressed.
Yeah, so actually, at some point, and if you know LitGPT, we always store it in PyTorch files. And at some point now, when R1 came out, I took all the safe tensor things and made one big dictionary out of it. But of course, you can't load that with torch load, but the lazy loading works quite nicely.
Yeah.
And the thing that kept me changing it was that in the end, you want to distribute it across machines, and so having one large file is not so good because you don't
need to copy a lot of stuff across machines. Yeah, of course.
Just getting
we have the
data
freedom
to the
do
machines
that
is also a chore if it happens at scale, right? And then what Thunder does is you have the transforms. And so the transforms can say how to make a state dict from before the transform into one that's after the transform. And it will do so module by module.
Actually, it's not what I drew is not correct. Go ahead. Because it's the transform.
And this is kind of the thing that you don't want to materialize all the tensors at the same time. Exactly. And so it does this submodule by submodule, which usually works quite well. You might run into trouble when you're really, really, really pressed for memory, but that's another topic. And so with this, for example, if you do this sharding, you load one linear weight, and then you shard the weight in the transform, right? And so it will shard one weight at a time, and it will not need to load the entire memory and then shard all the weights. And so this works nicely when combined with the lazy loading.
Yeah. And so essentially each rank has already a reduced, when it's time to materialize, it already has a reduced model to load.
Right.
Yeah. And so after all the transform, you only have to materialize from this data, you will materialize only the part of the model that you are actually going to use on that rank.
Right.
Or going to store on that rank. You use a lot, but as we did explained earlier. And then we have the trace, right? With the trace, and the trace for each rank, right? Because we have many of these, one for each rank, and they will hold different sets of parameters. Now, the trace is the program that runs on each rank, and the trace will also be transformed to insert all this communication, right? And the synchronizations here. So before applying the FSDP transform, there's no communication in there. And note, we are not using Python hooks, right? PyTorch hooks to do that, whereas the previous FSDP does it, right? Here we have the computation that is not distributed, right? The straight line computation, and then we iterate over this computation and say, okay, now how do I augment it with distributed calls so that we do the synchronization before the computation? Or synchronizations, not like the gather before the computation. And the same thing we need to do for backward, right?
Yeah, and so that has a parallel. You have this for forward and backward in the computation, the communication. But here you also have a thing. I mean, you have the model sharding. The model will get sharded too if there is anything in there. If not, the meta tensors will get sharded if you want, like they get a different size. But so then at the end you want to get the full checkpoint again, right? You don't want to store it separately. And so the transforms can also define the reverse thing, and that will actually do communication because it will grab the parts that each machine has and put them together again, submodule by submodule, in order to then store the state dict. And there also is a way to store things incrementally while you're doing the state dict, right?
Yeah, exactly. And all this happens without involving users' code in any way, right? So let's maybe take a look now at the code, and then we can maybe run just a small example, and we'll get to a bigger model the next week. But maybe we can run through the implementation really quickly on GitHub. And
you want the implementation first or the example first?
Maybe the implementation first, since we have it fresh, and then the example.
Okay, let me try whether I'm allowed to share the.
Oh, if not, I can share it. Yeah.
No, I can try to share my window, and it's not clear. It usually, I don't know. It seems to not work, but it's okay. I will just switch to the right tab. So here's the transformation, and it is quite an elaborate one, but basically it's the transform class here, and it takes various parameters and also tries to get some things automagically, and then we have several parts, right? And here's the transform module. And it first needs to grab the thing that is its rank and the world size, which is how many machines are working on. Sorry about that. How many machines are working on something. And then it will go over the parameters and see which ones it needs to materialize if they are on the meta device or not, or which it places on the devices. It will, by default, if it gets meta parameters, it will just Thunder annotate them. Sorry. And then it will shard parameters. It has a broadcasting thing, but the thing we want is the sharding. And this basically happens here, where you compute the new shape by calling a utility function shard tensor. This will take a tensor and just grab the slice that we want, right?
Based on the rank, of course,
Yeah,
each node has a rank, it knows what to retain. Yeah.
And all these things, right? And
so to clarify, all the ranks will have the same parameter in the same in the size, and the shape will be the same, but the content will be different because it will be a slice of the full parameter that will be needed for computation, but that nobody holds permanently.
Yeah. So this is also something that we need to adapt to whatever communication primitives we have, right? And so the communication requires all things of being of the same shape, and so we pad as necessary.
Oh yeah.
And then there's the transform state dict for the submodule, and this goes basically for one submodule that is named here. We basically shard all the sharded parameters. It's not like rocket science. And that gives us the new state dict. And then we might do like the next thing, right? And there also is the reverse transform state dict. And this
which is used for saving, we remember from before.
Right.
When you have to save a checkpoint, what you need to do is to gather everything and write it, right?
Right. And so this just called the all gather, and for technical reason, it's the implementation of the symbol that we have. If you remember the extension things, the distributed primitives are the operators that extend Thunder.
And then we move it to the CPU because we don't want it, as we accumulate more and more unsharded parameters, we don't want them to fill up our GPU memory, right? So we'll just move them up.
So one thing that is interesting is that you actually get the state dict. Well, yeah, okay. So yes, so you can move it to the CPU, but imagine that there is on the Thunder module, there is a utility function that calls all of them, and then at the end you have the state dict that you put things into. And there you can make a state dict that saves the tensors immediately and just
on demand. Yeah, because otherwise you would run out of CPU memory. So you have the optionality to do one or the other.
Right. So that is something where you can build the components so they interact nicely. And then of course we need to transform the traces. And this happens in the transform traces pre-prolog as usual, because we need to adapt the prolog before running it, right? And so this is a bit more elaborate.
Yeah, I want to explain this. We need to adapt the prolog because, as you remember, the prolog checks shapes of inputs, but our inputs now are sharded, right? The inputs as in weights, because our inputs are also the weights. And so if the inputs are sharded, if the weights are sharded, it means that the original computation that we acquired was not sharded because it ran on the full sets of parameters. So we need to modify that to make sure to make the prolog aware of the sharding.
Right. And so basically you need to change the arguments of the checks in the prolog to adapt to the new shape, right? And the Thunder device. And so this is what we do. And then we also need to adapt the full trace, the computation trace. And basically what we do here is that we put in the synchronization. And now I need to, so it's this, I think
it's a visitor transfer. It's a bit more opaque.
Yeah, it goes through a visitor transform here. And so this is what creates in the end the
let's take a look because it's interesting,
so the
right?
Visitor, I really think this should eventually be consolidated, but where's the visitor?
It's above.
I love this new GitHub UI where everywhere you click, it's going to do something.
Oh, by the way, you might be interested in this. No, I'm not. I'm just clicking.
Do you want to buy a fridge for some beers to cope with this? But so what we do here is that we visit. But is this only the unpadding, or is this the entire thing?
Unsharded and padding. Yeah.
Only the unpadding, right? So it's here. It does a get item call, but it's not the thing that. Sorry.
Okay. This will unpad, meaning if we padded before, it will discard the padding so that we can put them together.
Right.
And then we can add the
so this actually happens earlier. So this happens here at the at the beginning. While we're doing the prologue, while we are updating this was the lines that we showed. And there's just a single line here in between where we do the synchronization for the sharded parameters, right?
Yeah. This is a primitive, right? So we will call our trace after this will have distributed primitives that will do the exchange. So maybe we can go and look at the example now. So we'll set the stage for next week.
So we share this tab. Do you want the example coded from scratch, or do you want me?
No. Let's just
try the rehearsal.
We're up on time.
Yeah. So which one do you want?
Which one? Yeah, the simple one.
The
just not from scratch. Not from scratch.
Okay. So let's look at this pre-prepared thing then.
Yeah.
And let me open two of them, and I will tell you why in a bit. So basically what we do is we get the process group here from, now I need to, we get the process group here, and I just took 2. I could have done 8 because I got this fancy multi-GPU thing here. But, so we have, we initialize the process group, and let me restart these just in case. And so you see that this doesn't finish until all the things run. So one of the core assumptions in most FSDP code I've ever seen is that basically everything runs the identical steps, right? The nickel primitives, which we use for communication, they will use things that expect to have the same call on everything. This is different to other types of parallelism, like the pipeline parallel, where you have a sender and a receiver. But so here that it's always some sort of symmetric exchange, right?
Yeah, and when this is not verified, usually the code hangs. And so when somebody comes to you and say, "Oh, nickel hangs," it's mostly all the time because you're not executing exactly the same program. Yeah.
And so what we have here is like a very simple model, 2-layer MLP, and we materialize it on the meta device.
Yep.
And the inputs will be on our device because everyone in the data parallel, everyone gets their own inputs.
Yep.
And then there's our two transforms. One is the FSDP transform that we just looked at. And then there's the materialization transform. And I'm cheating here because I'm just using the original module init. Usually you would do this differently, right?
Maybe we can cover it in some other, maybe next week, because it will have a problem on how do we load it, right? So for now, it's just initialized from the full model.
So this will be run on both GPUs, so we can do this. And then, of course, we JIT our model, and we can then see what's going on by printing the named parameters. And here we see our original module was 1024, 4028, and then it had 2048 to 512. And along the first dimension of the weight, this is like you have to switch the numbers to get the weight shape. You have halved sizes.
Yep.
Right? So if I compare this to the original model, so M, I can just copy this. If I compare this to the named parameters of the original model, you see that it was always in the first dimension, it's twice as large, right? Because we started this to 2. And so then when you run it, it hangs.
It hangs, of course.
Yeah, but that is, of course, because we don't need to run it on the other machine too.
Yeah.
And then you see that both get their output, right? And so this is all that happens. It's really easy. But
can we take a look at the trace?
Yeah, of course.
That would be interesting, right? Because we expect the trace to have some communication primitives in there.
Yeah, I didn't rehearse whether it is. So let's see if there is any. If not, it would not have hanged, so it's good.
Yeah, exactly.
Okay, so here we see that indeed and Thunder automatically sorts the communication to the top, which is good, but we will see whether it causes problem. Well, you need to bucket it, because if you sort it all to the top, you might run out of memory. You need to be memory conscious here, because basically if you gather all of the sharded things,
it's like non-sharding, right? Why are you even going through the trouble?
Then you will run into trouble, and we will see whether we do this right or not next time.
Awesome. Yeah, of course, because if you have enough memory, you might as well gather as soon as possible, because then you will compute, and then it's the quintessential computation overlap, but not if you run out of memory. So you have some leverage there. Anyway, this is great because we see the sausage of FSDP unraveling before our eyes in the trace, and that's the way we like it, and the way we can actually optimize it. And then we can also run backward, but maybe we'll see it the next time because it's super late.
Well, we can we don't run the backward, but we can tell the trace, right?
Yeah, for sure. So, let's do that. So what's the backward of
what's the backward
collective operation?
Synchronization.
Yeah.
So basically we start very, very reasonably, but then there's the reduce scatter prim implementation. And then at the end, we wait for everything to arrive. So we start the communication as early as we can. And then at the end, we just say, now we need it.
And one nice thing is that, like in FSDP, in forward, we gather, right? We call all the parameters. In backward, we need to do the reverse. And so we scatter. So it's very interesting. Maybe next time we'll see this in a bit more detail. Anyway, it was great. It took a while, but we got there, and we're getting really close to GTC. So next week is the final week. We'll have our talk. On the next Thursday at GTC about Thunder. So I'm very excited about that, and we'll also meet there, which I'm even more excited about. And have a great weekend.
Yeah, you too.
Bye.
See you all.